Isomers and stereochemistry. That's going to be the topic of this lesson. And we're going to start with an overview of isomers in general. And we got a lot of vocabulary to go through in this first lesson. We're going to lay a really good foundation for the entire chapter. But we'll talk about such terms like chiral, achiral, optically active, enantiomers, diastereomers, racemic mixture, meso compounds. Just lots and lots of vocab in this first one. And you got to kind of know the denotations, kind of like the textbook definitions. But you also need to know some connotations, kind of like how to recognize these in context and which molecules kind of have these certain characteristics and things of the sort. So a little bit of a pain in the butt, but we're going to work really hard in this first lesson to kind of pave the groundwork for the rest of the chapter. Now, in the rest of the chapter, we'll talk about absolute configurations. We'll identify R and S, or assign R and S, as we say, to chiral centers. We'll talk about molecules with multiple chiral centers and how we sometimes represent them with Fisher projections. We will then move on to comparing molecules and figuring out, is there some sort of isomeric relationship between these molecules? And then, how many different levels of classification can we get? How specific can we get in identifying that isomeric relationship? After that, we'll kind of do a couple unique things. We'll talk about molecules that can be chiral without chiral centers, and that probably means nothing to you right now, and that's okay. Then we'll finish the lesson off talking about what's known as optical activity. Now, for those of you that have already seen maybe some lectures on this topic in your course in college or something like that, great. Some of these terms might sound familiar. And for the rest of you, just know lots of vocab coming. And by the end of this series of lectures for this chapter, hopefully all these things are much more familiar than they are right now. Now, if this is your first time to the channel, my name is Chad, and welcome to Chad's Prep, where my goal is simply to make science both understandable and maybe even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I release a new lesson. All right, so we'll start here with an overview of isomers. And so first of all, you got to realize that for two compounds to be isomers, they can't be the same compound, but they've got to have the same chemical formula, so the same number of each type of atom for them to be isomers. And these come in two varieties. We come constitutional isomers and stereoisomers. And you got to kind of know the difference. Now, constitutional isomers, which are also called structural isomers, we say they have a different bond connectivity, so a different bond connectivity. And so a good example here would be like giving you this guy here and this guy here. These both have the formula C3H6. But they have very different bond connectivity. Here you've got 3 carbons in a straight chain, whereas 2 of the carbons are joined by a double bond, so a sigma and a pi bond. Whereas here we have no pi bonds, and instead of a straight chain, we have actually those 3 carbons in a ring. But both of these have 3 carbons, 6 hydrogens, so they're isomers. They're not identical. And the atoms are bonded in a totally different way, so a different bond connectivity. These are constitutional or structural isomers. Let me give you a little more subtle example here as well. So say I give you these two as well. They both have the formula C3H7Cl. And in this case, we've got 1 chloropropane and 2 chloropropane. And here chlorine is attached to carbon 1, and here chlorine is attached to carbon 2. And so the atoms are bonded in different ways. They have a different bond connectivity, and once again, these would be constitutional or structural isomers. Now, like I said, we're going to actually spend the bulk of the chapter talking about these stereoisomers instead. And the difference here is that your stereoisomers are going to have the same bond connectivity. What's going to be different, though, is the 3-dimensional arrangement of the atoms. So all the atoms are going to actually be bonded to the same atoms, but how they're kind of related to each other in 3-dimensional space is what's going to be different. And you've already seen an example of a stereoisomer, and that was our cis and trans isomers. So if we look at cis and trans isomers, you guys saw that with cyclohexane. And you found out that if you had 2 substituents, and here I made them both methyl groups, but they could be 2 different groups as well. But you found out if they're attached to cyclohexane with both wedges or both dashes, or if you drew it on a chair conformation, both up or both down, they would be cis to each other. And then you found out if one was a wedge and one was a dash, or one was up and one was down on a chair conformation, that would be trans to each other instead. And if you look at these are not the same molecule, it turns out. They have exactly the same formula, but you can also see that all the atoms are bonded to exactly the same other atoms. They have the same bond connectivity, we say. So 6 atoms in a ring where carbons 1 and 4 are bonded to methyl groups. 6 atoms in a ring where carbons 1 and 4 are bonded to methyl groups. But the 3-dimensional arrangement of those atoms is indeed different. So cis, again, where they're on the same side, these 2 methyl groups are closer in space than these two methyl groups, which are trans to each other. So again, same bond connectivity, but different three-dimensional arrangement of the atom. Cool, so those are your cis-trans isomers. Now, it's not just cyclohexane, but these can come with any cycloalkane. And again, the two substituents don't have to be the same. They could be different as well, and you're still going to have this cis or trans relationship possible. It turns out it's also possible with alkenes. So in this case, we've got cis-2-butene and trans-2-butene, which if you're on pace with this class, you have not learned to name yet. But in this case, you've got 4 carbons in a chain, 4 carbons in a straight chain. You've got a pi bond between carbons 2 and 3, pi bond between carbons 2 and 3. But it turns out these don't have the same three-dimensionality associated with them. So if you've got a carbon-carbon double bond, it means you've got a sigma and a pi bond. And that pi bond is the result of the sideways overlap of p orbitals. And so if you try to rotate that bond, you would break the sideways overlap of those p orbitals. And so it turns out that pi bonds you can't rotate. So you can't rotate a double bond. And as a result of not being able to rotate this, we actually have these two different possibilities that can't interconvert because the bond can't rotate around to allow them to interconvert. And we call these, again, cis and trans isomers, just like we did up here. They have the same bond connectivity, but a different three-dimensional arrangement of the atoms. Now, if we draw in the relevant hydrogens here on these sp2 hybridized carbons, it'll get a little easier to see what's going on here. So in this case, we like to say when you've got the two like groups right next to each other, only 60 degrees apart, that's cis. So here, whether you look at these two hydrogens, or in this case, these two methyls, we can see that they're only 60 degrees apart, and that's cis. So however, in the next example, you can see that these two methyl groups are 180 degrees apart, or you could look at it, the hydrogens the same way. The hydrogens are 180 degrees apart. So, and that is referred to as trans. So not all alkenes will be capable of cis and trans. So it turns out each sp2 carbon, besides the double bond, has to be bonded to two different things. That's a methyl, that's a hydrogen, they're different. So far, so good. Look at the other sp2 carbon, that's a methyl, that's a hydrogen, that's two different things. So there's going to be cis-trans isomerism. So, but the moment you make, either side of this have two of the same thing. So let's say I erase this methyl group and put another hydrogen there, well, this guy wouldn't have cis-trans isomerism, because now I would say, well, am I comparing these two? Well, that's cis, but these are the same as well, so that's trans. Well, then it's neither, because there's not two different ways this guy could exist. But got to put that methyl group back to make sure that cis-trans isomerism is possible. So for an alkene, cis-trans isomerism is not possible if either sp2 carbons bonded to two of the same thing. So it is possible, though, if both sp2 carbons are bonded to two different things. And it can be the same two things on this side and the same as on this side, but as long as each sp2 carbon on its side is bonded to two different things, it will have cis and trans isomers that are possible. Okay, so that's cis-trans isomerism, and this is not super new. But the next part is going to be a little bit new, and these are isomers that have what are called chiral centers. And this, again, we're kind of whittling our way to the most important part of the chapter, and this chapter really is going to center a lot around these chiral centers. Cool. So before we talk about chiral centers, we have to talk about what the word chiral means. And so chiral refers to when you compare something to its mirror image. So if I take my hand, it's our classic example, my right hand and my left hand, you can see that they are the perfect mirror image of each other. Now, they're not the same, though. So like if I want to, play baseball, if I want to get, a right-handed glove versus a left-handed glove, I have to get two different gloves, one for each hand. They don't, a left-handed glove would not fit on my, my other hand, and my right-handed glove would not fit on the other hand as well. And so because the hands are different. Now you might be like, well, you can line them up this way, and you're right, because they're mirror images of each other, but they're not exactly the same at all. They're not superimposable, we say. And so when you've got two objects that are mirror images of each other, but are not the same, we say non-superimposable is the word we use. I like to use the word non-identical, but non-superimposable is kind of the one we really like to stick with organic chemistry, but I'm going to use them both quite a bit today just to remind you that non-superimposable means non-identical. And so when you have two objects that are mirror images, like your hands, but are not the same, non-identical, non-superimposable, we say that your hand is an example of an object that is chiral. And so However, if you take two objects and compare them, and let's say they're mirror images, but they're identical, so then that's going to be an example of something that's achiral. And a good example of that would just be a blank sheet of paper. If I had a blank sheet of paper in one hand, another one in the other hand, they would be both mirror images and identical. You couldn't tell them apart. So as long as there's nothing written on them at that point. And so a blank sheet of printer paper would be a good example of something that is achiral. And so now we have chiral and achiral, and it involves whether or not you're identical to your mirror image or not identical to your mirror image. If you're not identical to your mirror image, you are chiral. And if you're identical to your mirror image, you're achiral. Now let's take a look at how this applies in kind of the molecular world here. And so we're going to take a look at some little models. And for this to make any sense, we're going to have to zoom in. All right, now you're going to have to put up with my big head filling your screen. I apologize for that. But I've got two molecules here, and these molecules are perfect mirror images of each other, and you can kind of see that if I start lining them up. So you can see that they are perfect mirror images of each other here. So line up right along a mirror plane, we like to say. So in every respect. Now the problem though is that if you try to actually overlap them, you'll see that you can't. Now I can overlap, the bond on the top and the blue bond, but if you notice the red and the black are in opposite places here, and these are not the same molecule. So they are mirror images, but they're non-superimposable mirror images. They're non-identical mirror images. And so we could say that this molecule is chiral, or we could say that this molecule is chiral. So the word chiral can refer to an individual molecule, and it just means that this molecule is not the same thing as its mirror image. Okay, so that's chiral. Now we have the opposite word as well, and that's called achiral, and let's see an example of that. All right, so here I've got an example of compounds that are achiral, and we can see that once again, these are perfect mirror images of each other. So they line up right along a mirror plane here. So, however, though, if you actually start overlapping the atoms, they line up perfectly. All the atoms match in every respect. We say they are superimposable. And so when a compound and its mirror image are the same, identical, superimposable, that compound is achiral now. So again, chiral means that you and your mirror image are not the same. Achiral means you and your mirror image are the same. So, okay, let's go back and take a closer look at the chiral version. All right, so here we've got these chiral compounds, and these are rather unique. So in that, again, they're mirror images, but they're not identical. And this is going to have some interesting consequences. So it turns out because they're perfect mirror images, they have the same polarity. They have the same dipole moment, so to speak, then, which will also cause them then, therefore, to have the same boiling point, the same melting point, and pretty much almost every physical property you can think of is exactly the same. And that's a pain in the butt because we usually manipulate some difference between physical properties between compounds in order to separate them. Well, enantiomers is what these are. It turns out when you've got two chiral compounds, those two mirror image versions are called enantiomers of each other. So that's going to be our next key word here. So these enantiomers, these non-superimposable mirror images, are really difficult to separate. So they have the same boiling point, so you can't use like distillation to separate them. They have the same dipole moment, the same polarity, so you can't use some form of chromatography to separate them. So we have to get pretty creative in separating these enantiomers. So now I've got the chiral compound here on my right, your left, and I've got the achiral compound on my left, your right. And the question is then, what can we look at from a physical perspective that is the key to understanding why one was chiral and one was achiral, why one was different than its mirror image and one was identical to its mirror image? So, well, it turns out it's the presence of what we call a chiral center. So, and if we look at the chiral version of this, this has what's called a chiral center right in the middle. And a chiral center, which is also called, it's got lots of names, chiral center, chirality center, stereogenic center, asymmetric center. So is an sp3 hybridized atom in an organic chemistry. Most of the time we look at, it's going to be carbon, but it technically doesn't have to be, and it shows up every once in a while as something other than carbon. But most of the ones we'll see in this class will be carbon. But you have an sp3 hybridized atom, which makes it tetrahedral in shape, that has 4 different groups attached. And we call them chiral centers because if you have one of those, that's the single greatest indication that a molecule is probably going to end up being chiral, being different than its mirror image. Well, if you notice the achiral one we looked at here, it did not have 4 different groups. So again, with the chiral version, we had red, blue, black, and then the white, 4 different things. So with this guy, notice I've got a red and a black, but then I've got 2 whites. It's 4 things, but not 4 different things. And so this would not have a chiral center, whereas again, this one with 4 different things does have a chiral center. And having 1 chiral center makes this guy chiral. Having no chiral centers, this guy ends up being achiral. So cool. So these chiral centers, they're just called that because simply they're the single greatest indication we have that a molecule is going to end up being chiral. So usually if I'm trying to identify if a compound's chiral, first thing I do is look for these chiral centers somewhere in the structure. You're not always going to have a model in front of you. You're going to have to recognize it from, a good bond line structure or something like that. And so you're going to look for some atom. That doesn't have to be carbon again, but it often will. So some atom that's sp3 hybridized, it's bonded to 4 different groups. Now keep in mind, this is 4 different groups. It doesn't mean 4 different atoms. All 4 of those groups could be carbon atoms, but one could be the carbon of a methyl, one the carbon of an ethyl, one the carbon of a propyl, and one the carbon of a butyl. That would be 4 different groups, and that would be a chiral center. Now we'll find out there are some exceptions. Not every compound that has chiral centers is going to be chiral, but most of them will. And we'll have a special name for those exceptions a little bit later in this lesson. All right, I'm glad you made it through having my head fill your screen. We'll get back to doing a little social distancing now here. So we'll go back to these chiral compounds one more time. And so once again, it turns out these chiral compounds are, mirror images, but have nearly identical physical properties in almost every respect. It turns out except for one, and we call that property optical activity. And this is going to get a little bit weird, and it turns out it's a quantum mechanics thing. But we got to talk about what's first called plane polarized light. So light is, has wave-like characteristics, at least I should say. And this wave can be a vertical wave, it can be a horizontal wave, it can be a diagonal wave. And when you have unpolarized light, you have light that's directed in every possible orientation for its wave anyways. So, plane polarized light, you can shine that unpolarized light through what's called a polarizing filter, and polarizing sunglasses are an example of a polarizing filter. And what that polarizing filter does is it blocks out all of the orientations except for one. And so let's say I use a polarizing filter and it blocks out all of the different orientations except vertical light. And so after I shine it through that filter, the only light that makes it through is the vertically aligned light. We would call that plane polarized light. And so it turns out when you shine plane polarized light through, say, a solution of just pure water, let's just say it's not a solution, but just pure water, it'll come out the other side and it'll still be vertical light. Now, it turns out one interesting thing is that if I dissolve an achiral compound in that water, it will still come out the other side as vertical light. But if I dissolve a chiral compound in the water, it won't come out the other side vertical anymore. It'll either get rotated one direction or the other and come out at some other angle besides the vertical. So kind of a weird thing. And it turns out it gets even weirder. So if you have the 2 different enantiomers, if I dissolve one of the enantiomers in the water in one case, and let's say the light gets rotated off to the left, well then if I go and dissolve the other enantiomer in water at the same concentration, then it would now get dissolved to the left, to the right, my left, your right. So by exactly the same amount though, provided they were the same concentration. So the 2 enantiomers for this chiral compound, the 2 different enantiomers, they rotate this plane polarized light in opposite directions. So the first thing is that, chiral compounds are optically active, achiral compounds are optically inactive. And again, that just simply means that chiral compounds rotate plane polarized light, achiral compounds don't. So that's the first part. But that's the only way we really can, quickly distinguish between 2 chiral compounds. So in kind of a macro way is we just stick them in what's called a polarimeter and we just see which way the light gets rotated. So, and again, the key is those 2 enantiomers will always rotate light in opposite directions by the same amount, again, assuming they're in the same concentration. Now, let's say you took and dissolved both of those compounds in your water at the same time together in equal concentrations. Well, it turns out that solution's no longer going to rotate light. That would be an example of an optically inactive solution. Now, if you put one chiral compound or the other only, so you have an optically active solution, but put them in there together in equal concentrations, and the light doesn't get rotated anymore because half the molecules want to rotate light one direction, the other half of the molecules want to rotate the light the other direction, and so on average, the light's going to encounter an equal number of molecules as it makes its way through the solution, and therefore, on average, not get rotated at all. And so they give a special name to a solution that's got a 50-50 mixture of enantiomers, and that is a racemic mixture. Cool, so another vocab word, racemic mixture, 50-50 mixture of enantiomers, and a racemic mixture is not an optically active solution. All right, so let's get back to our discussion of isomers here. So In this case, we've got our lovely chiral centers here for stereoisomers. So we talked about cis-trans, but if you've got chiral centers, we're going to break you up into one of two types then. You're either going to be enantiomers, which is a word we have already used. And enantiomers, again, are non-superimposable mirror images. Only chiral compounds have enantiomers. Achiral compounds don't have enantiomers. Chiral compounds are different than their mirror image, and the two different forms are called enantiomers. Achiral compounds are identical to their mirror image, so they wouldn't have enantiomers. But the other type here are called diastereomers. And so enantiomers, again, so let's actually go back up to stereoisomers for a second. So stereoisomers, same bond connectivity, different three-dimensional arrangement of the atoms. And it turns out from stereoisomers, I broke this up kind of here, but technically a lot of textbooks will actually break this up straight from stereoisomers into this kind of dichotomy instead, enantiomers or diastereomers. If two compounds are stereoisomers, well, they are either going to be either enantiomers or diastereomers, it turns out. Now, enantiomers are stereoisomers that are mirror images of each other. And so guess what diastereomers are? They are stereoisomers that are not mirror images of each other. And your cis-trans isomers technically would be a great example of that. These are not mirror images of each other at all. And so they are not enantiomers, but they are stereoisomers. And so your only other option then is then stereoisomers that are not mirror images. And it turns out all of your cis-trans isomers are technically diastereomers. So, and this is something to file away in your head, because most of the time when we look at the word diastereomers, we're going to recognize when compounds are diastereomers in a different way for most of the examples. But you should remember that cis and trans isomers are technically also examples of diastereomers as well. And again, whether that's cycloalkanes or alkenes, same diff. So, but most of the time when we look at molecules that have chiral centers, we'll be able to identify them pretty quickly of whether or not the relationship, whether or not they're just the same, identical compounds, or whether or not they are some form of stereoisomer, either enantiomers or diastereomers. And there'll be a quick way to kind of figure out, well, are they, mirror images of each other, or are they not mirror images of each other? So for example, if we take a look at these two right here. So I've lined these up on right across what we call a mirror plane, or sometimes, actually we'll just call it a mirror plane. So this mirror plane right here, so you can see that the one on the left is the perfect reflection of the one on the right. So however, if you actually rotated this one around to try and line up the carbon chain, well, by flipping it over, notice right now that chlorine is coming out of the board. So right now it's coming out of the board. By the time I flip the whole molecule over to line up the carbon chains, that chlorine would be going into the board. And it wouldn't look like this. It would look like this instead. And those are not the same. They have the same bond connectivity. All the atoms bonded the same stuff, but the three-dimensional arrangement of the atoms is indeed different. And so in this case, they are mirror images, but I can see that they're never going to line up. And so the key here, though, in recognizing that these were enantiomers, is finding that chiral center first. So some atom, usually carbon, that's bonded to 4 different things. And it turns out that's this carbon right here. So this carbon right here is bonded to a chlorine. Okay, check. It's also bonded to a hydrogen that's not technically drawn in, and you should recognize that. There's a hydrogen right there. And then it's bonded to 2 carbons. But these 2 carbons are not the same. The one on the left is the carbon of a methyl group. The one on the right is the carbon of an ethyl group. They're definitely not the same. And so that's 4 different groups. That's a chiral center. And it turns out if you have one chiral center, you're chiral. Done. It's when we have many chiral centers that we'll see some exceptions creep in. But if you got one chiral center, you're chiral. No ifs, ands, or buts. Life is good. All right, so these are mirror images, but not identical. Life is good. One other thing you should know is that a chiral center is the most common example of what we call a stereocenter. And a stereocenter is just an atom where if you have 2 of the things attached to it, trade places, you get a different stereoisomer. And it turns out chiral centers are examples of these stereocenters. So it turns out if you take any 2 of the groups attached, any 2, doesn't matter which 2. Most commonly you'll see it be the wedge and the dash, but it could be any 2 on a chiral center. If you have those 2 groups trade places, you get the mirror image version of that compound. And so in this case, if you have the hydrogen and the chlorine trade places, well, then it's going to look exactly like this. The chlorine would be the dash. The hydrogen, which is not drawn in, would be the wedge. Now, I could have just as well have had the methyl and the ethyl traded places or something like that. So if I had the methyl and ethyl traded places, it would have looked exactly like this. But having the chlorine and the hydrogen traded places, it looks like this. But don't forget that this was the same thing as this, just rotated to 180 degrees around. And so the way we recognize enantiomers is oftentimes not by lining them up on a mirror plane like this, although that can happen and you should recognize enantiomers that way. But oftentimes we'll recognize it by looking at chiral centers and seeing that two groups have traded places. Trade two groups on a chiral center, you get the mirror image version of that chiral center. All right. So now we've seen a couple different ways we recognize this. And so again, the definition, enantiomers are non-superimposable mirror images. But the way we'll often recognize them is by looking to see if two groups have been traded places on a chiral center. And we'll find out that a compound with many chiral centers is you'll have to invert every single one of those chiral centers to get the mirror image, the enantiomer. And so even if you can't quite see the mirror image at that point, they're still mirror images. So like right now, you can see that my hands are mirror images. Now, if I do this, and something like this, you might be like, well, are they mirror images or are they not? Well, obviously they're my two hands, so they are. So except for where I, punched a wall when I was like 18 and broke my hand and there's a big bump here. But outside of that, these are perfect mirror images. So, and again, even if they're not lined up in such a way that you can see that they're mirror images, they're still mirror images. So same thing here. If I give you these two right here, you're going to want to get to the point where you're like, oh, they had just the wedge and the dash trade places? That's the reverse form, the inverted form, the mirror image form of that chiral center. When you have any two groups trade places on a chiral center, you're going to get that mirror image form. And so even though if I compared these two right here and said, how are they related? Well, you can't see that they're mirror images very easily, but now you've learned a new way to recognize that they are indeed mirror images. Even if I can't see it right now, I know that they're mirror images and they are enantiomers. Okay, so let's talk about diastereomers for a second. And so once again, just a reminder, cis and trans, those are diastereomers. But the new type is you're going to see that diastereomers most commonly are going to show up in the context of having many chiral centers. So let's say I give you, actually let's go here. Let's say I give you this compound, and then I'm going to give you its perfect mirror image. So you have to first look and say, okay, are these compounds mirror images? Yeah, that's the perfect reflection of this. Do they have chiral centers? Well, yeah. Turns out there's two. There are two of these chiral centers present in this case. And we'll see that there's some new relationships possible here, but these are molecules that have chiral centers and they're mirror images and they're not the same. If you try and overlap this, and if I flip this over to try and get the bromine in the right place, by flipping it over, now the bromine would be here and the chlorine here, but they'd be dashed bonds, not wedged bonds. They're not superimposable and they're mirror images. These are enantiomers, so still under the enantiomers category. So, and the idea though is that you have to invert every single chiral center for that to be possible, or just draw them as mirror images like I've done here. However, there's going to be another option. What if instead I compared this one right here? If you look at comparing these two now, you look at these and say, okay, it's a 5-carbon chain. Bromine's bonded one end from one end, chlorine's bonded one end from the other end, so the bond connectivity is exactly the same. But I look and I say, are they mirror images? Because they're lined up in such a way that if they were mirror images, you'd see it right now. However, the reflection of a wedged chlorine should be another wedged chlorine, not a dashed one. Now the bromines look mirrored, but the chlorines don't. So these are not mirror images. So they are stereoisomers that are not mirror images, which means they can't be enantiomers. So then the only other option is diastereomers. And the definition is really non-superimposable, non-mirror images. So they're just stereoisomers that aren't mirror images. Cool. And that's what we see here. And so usually what you'll find is, I could draw this a little bit different way. If I rotate this one around and flip it over, so, and I'll do that in red. So same compound on the right here, I'm just going to rotate it out of the plane here 180 degrees. And see these lined up just a little bit different. You'd see that the chlorine lines up just like the one above it. But the bromine is now going to be a dash instead. So again, this is the same exact compound as the one on the upper right here. And so we already decided that these were diastereomers. Now I just want you to be able to recognize it in a different way. If you look at the chiral center on the left, the one that has the chlorine attached, it's in exactly the same configuration, the same three-dimensionality. There's no difference. Okay, but if you look at the other one, so one's a wedge, one's a dash. So they've had the wedge and the dash trade places. Here, the bromine's on the wedge, the hydrogen on the dash. Here, the bromine's on the dash, the hydrogen on the wedge. We've inverted it. Again, it's a stereo center. You trade two groups places, you get the opposite mirror image version of this. So we have one chiral center in the same configuration. We have one chiral center in the opposite configuration. And that's going to be the most common way you actually recognize diastereomers. You're going to have many chiral centers, and at least one of them needs to be in the same configuration, and at least one of them needs to be in the opposite configuration. That'll be the key. For two compounds to be enantiomers, it turns out, all of the chiral centers have to be inverted. They all have to be in the opposite configuration. But for diastereomers, at least one the same, at least one different, then they're going to be diastereomers. Now I say this, and students get used to recognizing diastereomers this way, but don't forget that cis and trans isomers, again, are also considered diastereomers. So there's one last thing we need to do in this lesson, and one of the common questions you'll get on this section of your course is they'll give you a big molecule and they'll just ask you to identify the number of chiral centers on the molecule. And so there's a couple tricks for how you do this. Now, one of the keys is going to be actually eliminating atoms that are definitely not chiral centers. So first thing you should realize that all chiral centers are sp3 hybridized. Again, they don't technically have to be carbon, but most of the ones, or even all of the ones you'll see, will be carbon. So, but technically, don't just, assume it can't be an oxygen or something like that. So we'll have to rule it out, but it has to be an sp3 hybridized atom. So again, a chiral center is an sp3 hybridized atom, a tetrahedral atom, so with 4 different groups. So as a result then, I can cross off all the sp2 and sp hybridized atoms. So this one's out, 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 this one's out. Those are all sp2 hybridized atoms having pi bonds, right? So they can't be chiral centers, so we'll rule them out. The next thing I'll go through and do is I'll take a look at some of the heteroatoms. Like, so in this case, this oxygen right here isn't bonded to 4 different things. Now, it turns out in some rare cases, a lone pair can count as one of 4 different things on a tetrahedral atom. That was a 3. 4 different things. So, however, this has got 2 identical lone pairs. There's not 4 things coming off that oxygen. He is sp3 hybridized, but he doesn't have 4 things. So we'll eliminate him as well. And so from here on out, it's just going to be comparing carbons. And so again, these carbons have to have 4 different groups. So next time I'm going to look and say, well, any carbon that's bonded to more than 1 hydrogen would not have 4 different things then. So because if you have more than 1 hydrogen, then they're going to be identical. So for example, like this is right here is a methyl group, a CH3, and with 3 identical H's, there's not 4 different things there. Same thing's true there, there, and there, and there. So, but they're not the only ones. It's not just CH3s. I can look for CH2s as well. So notice this guy's got 2 identical hydrogens, so he's not a chiral center. Same with this one here, and that's it. So then I'm going to just want to go through and look at what's left. So I got rid of all the sp2s. I got rid of anybody bonded to more than 1 hydrogen. So who's left? Well, we've got this guy left right here. This carbon right here, and if I look, what's he bonded to? Well, he's bonded to the carbon of a methyl. He's bonded to this carbon over here. He's bonded to this carbon over here, and then there's a hydrogen not drawn in. That's a dash. Well, the hydrogen's definitely different. The question, though, is what about all 3 of these carbons? Well, I can definitely tell that this carbon of the methyl is definitely different than either one of these carbons, but these carbons are definitely different as well. And you might be like, well, how do I know, Chad? Well, look, this one's part of the 5 and 6-membered ring, whereas this one's just part of a 5-membered ring and then some chain coming off. They're definitely just bonded to different stuff. Now, one of the other things you can do sometimes, students often struggle for some that are like bonded as part of a ring. Well, as part of a ring, so for them to be equivalent, you could line up a mirror plane. So, and the entire right side of the molecule would have to be exactly the same as the left-hand side of the molecule. So for 2 atoms in a ring anyways, for them to be equivalent. And the right side and the left side of this molecule centered around that chiral carbon are not the same. So these are definitely different carbon groups. And so as a result, this carbon's bonded to 3 different types of carbon groups and a hydrogen. That's 4 different groups. And he indeed is a chiral center. All right, we'll go over to this guy as well, and he's also going to be a chiral center. He's bonded to the oxygen right here. He's bonded to a hydrogen as with a wedged bond that's not drawn in, and then he's bonded to these 2 carbons, and these 2 carbons are definitely not equivalent. This one's part of a ring, this one's not. This one's got no H's, this one's got 2 H's. They're just different. And so as a result, that also is a chiral center. And then we'll move on to this carbon right here. And this one is bonded to this carbon, this carbon, this carbon, and then again a hydrogen as a dashed bond. And in this case, I can see that this carbon is not the same as this methyl carbon. So that's cool. This carbon's bonded to two methyls, and this just is a methyl. And it's definitely different than this one as well, because this one's a CH2 that's bonded to, the rest of the molecule and stuff. So all three of these carbons are definitely unique. That's three different types of carbons and a hydrogen. That's four different groups. And that is also a chiral center. And then last but not least, the only carbon we haven't looked at is that guy right there. But this guy, and this is the tricky one in this example, this is the one where I'm expecting to fool a few students. So this carbon right here is actually bonded to a methyl group right there and another methyl group right there. Those are both methyl groups. And so this is not a chiral center. Now, a lot of students will learn this and they'll say, well, just look for wedges and dashes, because if it's a chiral center, then they have to show the three-dimensionality of it. Which is typically true. And sometimes they won't show the three-dimensionality and still expect you to identify as a chiral center, but oftentimes that's exactly right. They're going to show you three-dimensionality so that, because it, technically could exist in two different mirror image forms, right? And so if they're showing you three-dimensionality, that's a key of also where to focus in, but don't forget to rule some other stuff out. And also don't fall for this trick right here. It's not just that they show you three-dimensionality, you still have to verify that there's four different groups. That was not the case here, and so he wasn't a chiral center. And so overall, we can see that this molecule just has a total of three different chiral centers. Now, if you feel like you learned something from this lesson, consider giving me a like and a share. Pretty much the best thing you can do to support the channel. And if you're looking for the study guide that goes with this lesson, or if you're looking for practice problems and you're really going to want to do a ton of practice in this chapter, but consider checking out my premium course on chadsprep.com.